Hello, everybody. My name is Kevin Kawchak. I'm the founder CEO of Chemical Q Device, here for discussion 123. So this is QiML 2.0, speed up scalability and performance for the software for the new machine learning era. So I started off basically with this is to show a table of what's going on. So many people are aware of quantum-inspired techniques, and you hear about it in the news. And I wanted to go over what's been used primarily in the objectives for, say, quantum-inspired machine learning 1.0, is it is classical machine learning software, and it was developed as a tool for future quantum computers to use, and this never really took place. And it's safe for processing sensitive data without quantum noise, and it's basically aims to be an exact simulation of quantum systems and quantum circuits. Now, the way that this is done is basically you deal with classical data, it gets embedded, that takes time and cost into quantum states, and then you do some form of machine learning with these parameters, then it's measured back into classical information. Now, what was experienced by and large, myself and others with this, is slow run times for studies and only about above average results, and exponential RAM limitations, even going from like 20 to 30 qubits. So by and large, like I said, it was more of a tool, for if quantum computers ever did come around to use. And it lacked access to complex systems and high qubits, and that would still be the issue today. And there's basically no opportunities for big data applications just because there's so much going on between turning classical information into quantum states and then measuring and then going back. And that happens every single, mini batch or multiple epochs of machine learning. So what it did is it gave us insight, further quantum insight to use. And there were many papers on this. If you search for state vector algorithms, variational quantum circuits, variational quantum algorithms, parameterized quantum algorithm or parameterized quantum circuits, many papers limited to small models. So when I'm talking about these are the majority of the Qiskits and the penny lane models that use these exact methods to try to simulate what a quantum computer could do. However, it did pave the way for new classical methods and basically different ways for people to think about the technology. And it was never really optimized for classical computers. It was more like to say, if we could only do this on a quantum computer. So with QiML 2.0 is basically it's still classical machine learning software. There's no other hardware, there's no quantum computer or anything like that. It improves on previous iterations of QiML 1.0 and other, quantum computer experiments. It's also safe for processing sensitive data or patient data or medical data. There's no quantum noise involved. And we'll see. So the key difference is that instead of trying to say like, I want to do this according to this exact quantum circuit, now we're using approximation of quantum systems and circuits. And in industry, the way all this will go is finding the ones that are fastest or give the highest performance, as opposed to try to get the most faithful representation of a quantum circuit for a specific reason. So classical data is processed with classical algorithms inspired by quantum mechanics and computing. Dequantized algorithms significantly have been shown to improve this gap between if there were a quantum computer to run a quantum algorithm and a classical algorithm that's this quantum inspired one, and it's a lot more convenient to use for many applications. So we'll talk a little bit about Ewin Tang's research, her dissertation. And then also with tensor networks, there's considerably enhanced accuracy, precision, scalability over other previous tensor networks, and it's a very hot field inside QiML 2.0. And then over the quantum computer experiments as well. Now, on state vector algorithms, I don't believe they'll be completely replaced because they are exact, or they try to be exact, which means RAM intensive, which means you can't ever get to access to these huge problems that we can get to, say if you use dequantized algorithms or tensor networks. And there's a variety of software techniques. If you've joined before, you'll see this as far as, circuit cutting, mid-circuit measurement, and a variety of other ones that you could do, qubit reuse, these types of things. And, we're already seeing approximation methods such as tensor networks trying to help out state vector algorithms. But the limiting factor there is you always want to have, classical. So be inspired by quantum, but everything to run fast efficient and high accuracy with less and less of, say, quantum states and embeddings and these types of things. So it removes many of the computationally inefficient steps. And then this is in specific is for speedups, scalability, and performance. Now, the table I marked here as quantum-inspired transition to dequantized algorithms, tensor networks, and large state vector algorithms. So that's the new kind of terrain here. Are there any questions regarding this? And then, so you can't talk about quantum-inspired machine learning without talking about Ewin Tang's research. So this dissertation, so I think it was about mid to late last year, is basically a culmination of all her research that she's done. Now, on the left is basically what was believed to be the landscape for, potential quantum computers. And I don't think she started off as against quantum computers at all. And so all of these, basically were within realm of, having some exponential quantum speed up. And on the right is basically this line to the left are still cases, so sparsity-based quantum singular value transformation on the left that can still, potentially have some purpose on a quantum computer, but it's looking more like super polynomial in the case of topological data, or quadratic speedups, but it's not looking like anything exponential when people were first thinking about this. So getting into this is there's a whole variety of machine learning applications out there, and her research and other people's too have tried to address this. So the first one is recommendation systems that, say Netflix and Amazon use. And basically with this is like you have your favorite movies and there's certain weights. So a person might like, Airplane because of comedy, and then Jurassic Park because of action, and then, these different weights. And it gets a lot more complex to this, but this is just a basic thing. But what happens with algorithms, traditional regular classical algorithms that now is being addressed with dequantized algorithms. So what happens here is basically you have a specific problem, statement for recommendation system, and it's this 8.1. And with the speed up is you have the quantum algorithm and there's no longer any exponential speed up, but the gap represented between the fastest dequantized algorithm is known as the quantum classical gap. And in this one, I believe the most correct way of putting this is the quantum runtime for this problem is up to some polynomial factor, still faster for the quantum algorithm, but it can't get close to actually doing that, practically because of noise and decoherence and other issues too, and economics behind it too. And then so this particular one that she put in the dissertation is better than a previous one. And this B point is really important. I mean, there's also the goal there to find a product that is a good recommendation for a particular user. Okay, so we're talking about the core essence of, many, many industries of saying like, this is the algorithm to use for this specific reason. Now, Tang's work was the first to dequantize what was previously believed to be the strongest candidate for practical exponential quantum speedups for a machine learning problem by quantum computers. And this is by John Preskill in 2018. So all of this prior research to all of this going on has not been thrown away, John Preskill, Seth Lloyd, and others, because they came up with quantum algorithms themselves, and now perhaps unexpectedly are being dequantized for more practical, convenient use on, standard CPUs and GPUs or TPUs. And another one here is basically this supervised clustering. So if you have semi-supervised, it means that not all the points are labeled there, so you don't get as many, as good of results. And I guess that might be a little bit easier to use, but a little bit more towards performance is if you can label all the previous data. And this is the quantum algorithm that addresses that here. So it says actually, the quantum algorithm has a quadratically faster runtime of this, and then her fastest dequantized is this specific one. So it narrows down that gap, and it keeps getting better. So that if you see in papers the current quantum classical gap, and again, like the quantum computers aren't anywhere close to being run, a lot, or there's just way too much noise. So it's running these all on classical hardware that were first conceived by, many people know quantum algorithm authors, Lloyd and Prescott. So basically, in this specific case for supervised clustering, what it is the first algorithm is a simple swap test that was dequantized by Tang in 2021. And the second one is an adiabatic algorithm, some more kind of like annealing with no proven runtime guarantees. So that's where the expertise comes in this field, is even between different types of machine learning applications that are being used for dequantized algorithms. Some have a specificity towards low rank, and just it sometimes it depends on the problem itself, your data set, these types of things. And this next one's interesting. So principal component analysis, many people are familiar with in machine learning. And there was this 2021 World Happiness Report based on GDP, the social benefit of living in a specific country and your life with it too. So you can see the US is, situated somewhere in the middle here as being, better with GDP, but not the best, and, having some social and, so other countries have different benefits with it. So where it is with, and again, all of these were originally conceived to use in quantum machine learning by quantum computers with a quantum algorithm, but have since been substantially negated of having this potential of having any exponential speed up outside of very few cases. So here's the quantum algorithm here on the left, for the given problem statement for above. Here's the fastest dequantized algorithm here in the middle. And then a lot of times she would just improve on her previous work. And if you search for dequantized algorithms, everybody cites Ewin Tang. So she graduated at University of Washington. This is her PhD dissertation. And I think she's does stuff with Berkeley as well, UC Berkeley. You'll see she has a Berkeley email address and some of the other publications. So here's an example. So it says industry does not know how to dequantize protocol exactly, but can be dequantized in the low rank setting. So if there's low rank, to do it this specific way. So it's not always the case that you could just go across every single QML algorithm, turn it into dequantize. And like I said, it was unexpected that, basically it's significantly cut down on any future prospect for, I would say more so for quantum machine learning with quantum hardware because of the other issues related to the technology. So here we see, and this is more of the principal component regression, is when you have principal component analysis and you perform regression on it. So on this specific one, what is shown here is basically for this given problem 8.12, here's the quantum algorithm, which is typically written, it's the shortest, it's the easiest to read. And then here's the gap between these two. And they say the specific gap, the quantum algorithm using block encodings, okay, this specific, application of it takes up to polylog mn factors. And we've seen that before with polylog mn. So that's approximately how much on paper, the difference between the two. But again, the practical application is we can run these all day on, classical computers. And, you see this a lot, and it takes some digesting because it's not what you hear in mainstream news, right? You just hear very specific things and they say like, this specific area of the field is still in infancy, okay? But this has been built up, and actually Lloyd et al. And others and Tang in 2018 actually worked together. And I think at this point it was accepted that the dequantized algorithms are an appropriate way of going about using, actual quantum algorithms in a much more practical way. And then we have support vector machines. So the whole thing is if you have two binary classification with the boundaries here, and a lot of these pictures are very basic. So for a given problem, basically it says our algorithm. So this is the dequantized algorithm here, with a special SQ access. So these are two different, it's a different time complexity of the original runtime, but this SQ is it's a specific thing that's needed sometimes. And with this specific one, so sufficiently large, it's basically saying for the solution for this problem, this matrix aversion, is simply reduce, right? So this is another case that it's an effective use of a dequantized algorithm from a quantum algorithm. And then Hamiltonian simulation, you're going to hear a lot with energy and chemistry calculations and these types of things. So they say for this problem statement with a Hermitian matrix and a, with this specific notation, dequantizing it, there exists an algorithm that outputs a vector y such this, and this. So there's a lot of conditions that come by, and that's why you don't hear about it in the news, because it's hard to portray all of the different dequantized algorithm benefits in a concise paragraph, right? Because this statement on its own, requires an explanation. But here is the dequantized algorithm, for use in place of using the quantum algorithm. So and actually, in this specific case, it says that the author's algorithm is significantly slower than the competitors. The competitors' sparsity assumptions are essential for their fast runtime. So the practical use of it, I believe, is going more towards Tang's, specific algorithm. And again, she kind of leads the industry with dequantized. And semi-definite programming, basically another problem statement. And I chose to include the algorithm itself here. And, basically, so all of this is, you see a lot maybe 1997 to current day. In 2020, quantum-inspired algorithms could dequantize these quantum algorithms in certain regimes. So, this is the last one here. So this is discriminant analysis. And in this specific case, the quantum algorithm achieves this runtime. And I find some of these, in other surveys and reviews of this is the quantum algorithm runtime. And then here's the dequantized algorithm here, where it says problem 8.32 in, this specific statement here. And you'll hear these a lot. So Kong and Duan introduced a quantum algorithm. And I've watched a number of some of these lectures, including Seth Lloyd, and he'll ask people in the beginning, and he says, well, who here believes that we need more quantum algorithms? And I think that he's seen the process of this, dequantization on a lot of them. So it's not only trying to get some exponential speed up, but will it stand its case when it goes to get dequantized? Because it's a huge benefit if you can run something exponentially, and it's another benefit if you could do it practically on existing hardware, that we have today, CPUs. Are there any questions at this point? So feel free, and then during this, you can put it in the chat as well. Feel free to raise your hand as well too. So in all these papers here, it's QiML 2.0. So the clear distinction between QiML 1.0, which is what most people use, and 2.0 is 2.0 uses some type of software technique or approximation. So dequantized algorithm approximates a quantum algorithm. Tensor networks approximate a quantum system or a quantum circuit. And then a state vector algorithm would use some form of a software technique like circuit cutting, or use a tensor network to take over as opposed to being exact, right? And this is done to get to bigger solutions, bigger problems for higher accuracies that nobody got too far with, say capping out at quantum inspired machine learning at like 30 qubits. And this looks to be, we can go, higher now because of some of these techniques. So in this specific paper here, so it's quantum machine learning and tensor networks as an aid in the clinical diagnosis of coronary artery disease. So you see a lot of QiML papers with healthcare. They don't typically have the very, as far as being like, and I'll show you some like 3 papers after this. It's still good to use medical data with it. But in this case, it's 3-qubit MPS, 4-qubit MERA, and these are all tensor networks, 4-qubit TTN. And they say they got similar or better results than the best classical models compared to 6 classical machine learning models. And it's actually good. This paper shows that these are going to be compared in dequantized algorithms and, especially tensor networks, head to head against existing machine learning papers that aren't inspired by quantum physics or quantum mechanics. So the ones that they went head against was logistic regression, naive Bayes, support vector machines, decision tree, random forest, and XGBoost. Okay, so these were researchers, from basically across the world. And, this table up here, and they included many tables, but the one that was kind of like the money shot would be to that direct comparison. And if you want to go deeper into this, because it uses, the IEEE heart disease, Cleveland and Hungarian data sets, that's available to you. Okay. But this one here up top, it shows more of the comparisons between the different types of, tensor networks. So variational quantum circuit, MPS tensor network, and then rote. And then that's for the Cleveland's data set. And that was the best one of the bunch there. Okay, so that's kind of what I saw too, sifting through the tables is basically a little bit better, similar or better results than the conventional ones. And I would say it tried to do a lot of stuff, 3 different data sets. And, so we'll get into some of the ones that are perhaps a little bit more technically interesting. Now, piecewise polynomial tensor network for quantum feature encoding. This is what I was thinking when I thought of tensor networks, QiML 2.0 is basically having some approximation for this intensive encoding step coming from, classical data into quantum states. And what the researchers here at Fraunhofer, and then again, this is a 2024, is on the top here, encoding of the features into an MPS with a maximum rank of 2 and converting the latter to a quantum circuit. So as far as results, I don't think they went too far with this. And I think the main issue is they were intending to use it on some type of quantum hardware. But this is an example of something that can be purposed, for if you insist on running state vector algorithms, in QiML 2.0, they say convert tensor network gates to those native to non-classical hardware may introduce significant overhead. Now, we don't see that because we don't have, because we're classical data. And if you go classical to classical to classical, but if you do quantum states, these types of things, there's usually computational expenses where you're not, you can get better performance in QiML 1.0, but you're losing time and you can catch up on that time, in an efficiency sense of just using, other classical methods. But this one was interesting too, because and basically I'll have all these links up too, is it's, trying to assist the state vector algorithm, likely with speed or size, and, using it for encoding purposes. Now this one, and so the next two are really good. So this is NSF, MIT, Harvard study, and they call it bridging autoregressive neural networks, which is a thing, in conventional machine learning today, and tensor networks for quantum many-body simulation. So, there's many things that you can use tensor networks for, and people have already done. It's just the performance, when we talk about accuracy or model size or these types of things, or scalability in 2024, that's coming to light. We're starting to see these good results. So what the researchers did here is basically in this graphic on the left, this ARNN is something that's highly expressible, that exists in classical machine learning or deep learning. And then the one on the right, which is tensor networks, which is physics-based, physics inductive bias, with limited expressivity. So why not take the advantages of both? Because the one on the left is highly expressive, no physics prior. The one on the right, the tensor network, is physics inductive bias, but limited expressivity for this hybrid network, right? So no doubt they're probably working on other stuff too. And I think the results here were good. Now, it all comes down to your 101s in Hilbert space and these types of things that we talk about in, quantum machine learning. And the issue is if you go to purely simulate a full quantum circuit, in a classical computer, you're essentially wasting a lot of that, space time because you don't need it. You're only looking at a specific area in the Hilbert space. And that's where they say it's intractable to do this with direct simulation. So, the two limitations, as I mentioned above, expressivity and inductive bias, is trying to get the best of both worlds. And with this new one, this ANTN in the middle, that takes the classical machine learning and then the new, quantum physics-based tensor network, it says to parameterize normalized wave functions. And here was the thing, you can still do exact sampling, and it generalizes expressivity, and it inherits some of these symmetries that are widely available in this classical neural network architecture here too. So the two problems that they did is basically this: quantum state learning, finding the ground state of the challenging this 2D J1, J2 Heisenberg model. And they found that their hybrid model in the middle outperformed both tensor networks and autoregressive neural networks. And it opens up the door for, and this is a buzzword, such as mean field theory is a buzzword to use with tensor networks, is quantum many body physics simulation, quantum technology design, generative modeling, and artificial intelligence. So, it's hard to tell how big tensor networks will get. There's a lot of development, and I've kind of tracked this through, I've reviewed other tensor network, paper earlier last year, and the performance is not too good. So, when people have found to make these work, and especially a lot better, is when you start to hear that saying like deep learning, tensor networks, which one did you use? How did you use tensor networks to help deep learning or machine learning, those types of things. And they say their approach is robust, and it surpassed tensor networks with even large bond dimensions. So meaning the pure, physics-based approach or quantum physics-based approach or quantum-inspired approach, it did better than that. Now, this last one I have picked out because, number one, I heard that one of the speakers talk on this at QHack. By the way, QHack is finishing up today. And, typically they have a bunch of speakers related to quantum machine learning, quantum computing. They still had Jeopardy, quantum Jeopardy, and they just finished up, with some of the memes and stuff today. But, one of the speakers they had on was from Multiverse, and they kept talking about this. Again, it's not using the whole Hilbert space, in classical computing, because that would not be efficient. It's using only the portion to them that mattered. And this was with other researchers from Barcelona, Donostia International, and this Iker Basque as well, and this bigger paper. And the way the language is, the only downside with this is just a little short on the number of pages, but I think they were really trying to get this out. So basically what it does is you have like ChatGPT, well, we don't really mention, Llama is the one that they chose to compress. Okay, so taking Llama 2, 7 billion parameters to only 30% size, and they maintained over 90% accuracy. So what was the comparison is if you take traditional methods, and I think these are all compression techniques of pruning, distillation, low rank approximation to reduce the number of effective neurons, or using quantization to reduce numerical precision, that's been done. And what they're saying is using model correlation space, and I believe they're talking about Hilbert space, is it's a more effective way. Okay, so again, I think we'll hear a lot more of this one, and it was just a tad on the short size for an archive, maybe 3-4 pages, something like that. But what we see in the left-hand corner here is these are all given the original Llama 7 billion parameters, which is in red, or their 30% sized model, which is in green. So what we see here is for the gigaword, data set, that looks about, that's over twice as fast. So the green is over, twice as small as the red. Now the X sum, probably about that. Maybe it's, a little bit over, twice as fast for X sum. Now, this is time per epoch. So epoch is basically another measure of time, because the more epochs you run, the longer it runs. And then for sheer time, using these same two models. So red is the original Llama 2, 7 billion parameters, and then the green is their 30%. For forward time, this is machine learning talk here. It's basically, that looks to be maybe 3 times faster for the green, and for backwards time about twice as fast. Okay, so what we're talking about here is a model that by size is 30% of the original. And then on the time basis here, we could see it was, roughly between 2 and 3 times as fast as the original Llama 2. So if you're in AI machine learning world, Hugging Face, the whole thing, this makes sense to you, okay? So on the other side here too, and this is using the quantum physics inspired approach as opposed to these other traditional methods if you're just joining here. And on the right-hand side are all scores. So these are basically, scores are synonymous with like accuracies, these types of things. So again, the red is the original, and then the green is the 30%. It's 30% the size of the original. So it's over twice as small. And then, so we see it's very comparable. And here's where they said about 90%. So that looks like for many of these, 80 to 90%, I'll probably give it. And again, I think they just want to get this paper out because they thought that the results were so good. And again, so the further context with this is AI and machine learning models in specific are known to have billions, if not trillions of parameters. So if you can keep the accuracy at a acceptable rate while reducing the size significantly, and on the left, reduce runtimes of these AI models, and then on the right, keeping most of the score or the performance, then this is highly desirable because these are run so much. It's such a big thing because there's leaderboards with Hugging Face, and they'll say, well, how many billion parameters, or I'm on a advanced machine learning call on Saturdays, and these are the types of things that they talk about, the important factors of LLMs and numbers of parameters. And as accuracy increases, you don't want your size, or as model size increases, you want to keep the accuracy, but you don't want it to take up too much size, like storage size. Okay, so this was run on 8 A100 GPUs, and they say the compression rate to reduce the size of the AI model here is based on the tensor network bond dimension. Okay, so this is a familiar term if you've done tensor networks. And it provides a more refined, controllable, and explainable compression technique of these LLMs, right? So that's a huge buzzword when we're talking about, customer experience, patient experience, is basically, is it explainable? How explainable it is? How much of a black box does it have? Okay, so here's the last one. It opens the door to the development on premises of LLMs for entire new world of applications. Okay, and they said at one point for the democratization of deep learning, right? So if you can get the model size down, because say for instance, ChatGPT is trained on the entire internet, okay, but in medical world, if we want to use LLMs, maybe as soon as October this year, when they do announcements, maybe, is that we only want to train on, we don't need that huge a model, and we only train on medical, not the entire internet. So anyways, I would definitely check this paper out. If you haven't started following tensor networks, I would do so. The other news behind this is basically, in Australia here, Palsy Supercomputer Research Center to use NVIDIA CUDA Quantum. Pretty much all of industry, and with the abundance of all of the, the technical, advantage of using QiML 2.0, so that's QiML 2.0, and, industry is fully supporting it. And then academia, the papers keep getting better on the performance side. So basically they're saying a 10-fold increase in application performance when processing data sets measured in terabytes. Now we're talking big data. Okay, so if the model, if QiML 1.0 is not, compatible with efficient compute use, you can't use huge data sets, these types of things don't, it favors the QiML 2.0 basically. So Fujitsu, again, 200 times faster. This time they're saying they're distributed group computation. And again, I would probably put this onto software techniques and QiML 2.0. That's the main thing. And they're probably using approximate techniques. Tensor networks is so synonymous with scaling and, speed and these types of things. And I think that we'll see other good things with dequantized algorithms too, because they're so fundamental towards now replacing every quantum algorithm or many quantum algorithms into dequantized. So here we go. So at least 8 original quantum machine learning applications have been dequantized. So they're efficient to run classically. Usually it's between, polynomial slowdown, super polynomial, quadratic, those types of things. But it's still, light years ahead of, say trying to run on a quantum computer in like 5 years. So his recommendation systems all the way up to discriminant analyses, convenient and efficiency. And so tensor networks, again, are picked off because there's many people have wanted to simulate quantum systems and quantum circuits and to do it efficiently. And they've always been picked off as far as like, this is the technology to use. And now that the results are coming, not only from this week with that compression model in specific, and a little bit from the NSF, MIT, Harvard paper, and from last week too, with these researchers from New York University and Flatiron Institute, now they're saying, okay, we're getting really excited about it. We figured it out that they work now. So, these are the 4 different examples that I showed today. And again, these last 2 kind of having a little bit more weight to them as far as, on the technical side. Now, and then, we also see in industry, this continues to just strengthen and grow at a very good rate of using quantum inspired, algorithms and GPUs or TPUs and CPUs. So here's the references. And then one thing is everything's going to be pivoting because I think that this is technically established and it doesn't need a whole lot more on top of it to start talking about using it for increasing patient experience, these types of things. And it's a quote by Steve Jobs. He says, one of the things I've always found is that you've got to start with the customer experience and work backwards for the technology. You can't start with the technology and try to figure out where you're going to try to sell it. So obviously you need to have a technology. And then, I think the main story with this, and I saw this, in a couple places this morning, is basically, yes, we have to be, focused on value for, customers or patients, expectations, either matching or exceeding them, the level of care that they're receiving. And this doesn't have to be medical. You could just care for your customers and the environment too. So like, what is the environment of, QiML 2.0 suppliers, for algorithms or applications? What's that going to look like? So I included a bunch of that stuff. Are there any questions regarding a specific area in the conversation here?
Kevin, I just have one question.
Yeah, go ahead.
So, with respect to classification, one of the points you mentioned was on binomial classification. I was just wondering, in QiML 2.0, are we getting equally good results or better results with multi-class classification? Maybe for recommendation systems, but I was just not sure.
Yeah, I mean, so say for instance, I had this model, it's called quantum transfer learning. And if I got up to 44 classes of different types of brain tumor images, so there's no tumor, glioma, meningioma. And the requirement of the model would say I would need 88 qubits, which is 2 times the number of classes. And I could never get there. So you lose a little bit on the approximative nature of it, such as tensor networks, which are doing very good right now. But I think in order to run it properly, like how many models are set to say run in similar ratios, is that you have to use QiML 2.0. So what I presented on last week, and I think the week before, is actually IBM Quantum and IonQ have simulated a circuit using some software techniques to get up to 192 qubits. And, so that's been, paramount, because that we thought that we could only go up to like 60. So that was huge. But yes, you can't, because you're talking into like there's more RAM than what's available in the whole world if you want to do exact simulations with QiML 1.0. So yes, you'll have to use 2.0.
Oh, okay. But I mean, does it give equally good results on multi-class as well, classification?
Well, again, it depends on the model, right? So a lot of these,
Right.
there's different objectives. So in dequantized algorithms, there's already an established quantum algorithm for that quantum machine learning task that they took away the exponential speed up, and this is the best one to use now. So it really just depends. So something like quantum transfer learning, I could get up to, 44 classes, and, if I figure out the way basically to use approximation, so it's not using as much on the embedding, or with quantum states, and usually measurement isn't as bad. That's like the typical quantum algorithm process. Then yes, I mean that's what we're faced with. Is there are classical RAM restrictions, either geographically or across the world, and it's incorporating some type of software technique or approximation in order to do binary or multi-class.
Oh, okay. So thanks.
Any other questions? I saw some other people hop on here. So, the literature, the academic literature is very important because a lot of times in industry, you can't see through, the announcements that like Terra Quantum does or Classic does. And NVIDIA has gotten up to simulating tens of thousands of qubits using tensor networks with QTensorNet, if you're familiar. So, that's not machine learning, and that's probably not with a data set. That's just to say that we did it. So then where does that put us? And in my opinion, we should probably be, with all this news and papers, at least 90, because they did 96 qubits, IBM Quantum and IonQ, simulated on classical hardware in like 4 seconds. And that's just for the circuit. So then you bump it up with the data set, and you bump it up, resource requirements are going to get bumped up, and then doing machine learning optimization with parameterized circuits, those types of things. Any other questions? Yeah, go ahead.
Oh, no, I was just acknowledging. Also, I haven't really looked at this. Other than tensor networks, where do we tend to use the large state vector algorithms?
I'm sorry, I didn't understand the question.
The large state vector algorithms, there are different category as against tensor networks, correct? I haven't really explored those.
Yeah, I mean, they're typically
Right.
associated with, you have classical data and you want to convert it into quantum states, and that's like embedding. And then you're doing something on the machine learning side with parameters. So like, and these get adjusted over the course of machine learning to their most optimal values. But the problem is that that process has to go through every single time that the algorithm is run. And although it's exact, it's not getting people to good solutions because there's, the process is too restrictive. And again, it wasn't ever meant to be the awesome classical method for classical computers. It was always meant as a development tool if quantum computers would ever come around, because that's how they would run. Like in a quantum computer, they would run exactly. So, the thing about it is that it's been years and years, and I started this startup in October 21, and it just never came around. And even the new stuff, the new papers on hardware, just never did. So other industry experts, and especially academia, with tensor networks and ubiquitous equipment that we can innovate on, over and over and over. So you can't use tensor networks across the board if they're only limited to a couple people that have money, right? So you could do a lot of this stuff starting in, what was it, 2015, 2016 with TensorFlow and PyTorch on cheap collab stuff. The best A100 is only like $1.50 an hour. So that's the key with innovation and incorporating, and we're seeing this speed, especially with tensor networks, that it's going so fast on the performance side, and that's all enabled by a technology that has no noise. You could use sensitive data with it. So like I said, like this end Steve Jobs quotes, starts with a customer experience and then works backwards to the technology. Well, it's similar. Like if we have a goal in our head in industry, like we want to simulate this, thousands of qubits using, and a paper has said that they can get up to essentially infinite number of qubits with tensor networks efficiently, that it has to be run over and over and over again by many different scientists and checked and, peer reviewed, that whole process. So there's many added complexities with machine learning. And that's why, QiML 2.0 software with these approaches here is it works today, and it's getting a lot better with tensor networks, and the multiverse paper today was really good. Compressing AI models, to 30% of the original size. So it's stuff that I can now share in a machine learning group I attend on Saturdays. So I'll say, although you're not familiar with tensor networks or quantum inspired techniques, this is the different approach. It's not using some other known compression techniques. This is using like a spatial approach, like model space or Hilbert space, like a different way of programming.
Absolutely. Thanks.
Anybody else? So yeah, I think it'll be a very big field. Tensor networks in particular, they're just on that track of like, once there was all these papers saying we have great performance, then that was the main issue, because everybody knew they were efficient to begin with, especially if you use like MPS, but it's more restricted with applications over like a tensor tree or Mera or PEPs, these types of things. So people have figured them out, basically. That's what I'm seeing this year. And, it'll take a while. Like, who knows? They could get as big as deep learning, at how we see deep learning with convolutional neural networks and transformers and these types of things. So it's looking pretty good. And it doesn't look like there's much holding it back. And I would say, and feel free, so anybody feel free to put it in the chat, or you can come on too, is that with, dequantized algorithms, it's huge news. And then the next step is basically to take them into more and more applications, find additional literature. And there's other researchers besides Ewin Tang, but, it didn't just put the kibosh on, now you can't run your quantum algorithm on a quantum computer if it's less noisy in 5 years. I think that, the usable application for those 8 areas that I mentioned, that those and probably incorporating into other approximation methods too, tensor networks, state vector algorithms, these types of things. But the mindset for many years, basically in these Penny Lane demos and Qiskit demos, is you would have some quantum algorithm and you would try to faithfully simulate that exactly using state vector simulation. But nobody knew 100% and could kind of pinpoint that was the best way to get the fastest results and the performance. And with dequantized algorithms and tensor networks, it's a different mindset. So opposed to thinking about it not running on a quantum computer, it's saying like, there's some aspect of quantum mechanics and physics that we think is very interesting, and we think that will make it run fast on classical computers. So again, that's where people will have a hard time transitioning, is basically because, you have that strict mindset of specific algorithms. And I think what we're going to see a lot more, especially in industry, as it starts to make its way further and further in, is it's going to be less about those specific, that gates and these gates and those types of gates, as opposed to like, oh, okay, we have this dequantized algorithm, this tensor network, experimentally has been shown to work very well. So I think that's going to be the trade-off, right? So, and, if we're getting the results from, 2, and you can count the larger state vector algorithms with software techniques as 3, but it's not as strong as the other 2, right? As far as the case, because 192 qubits, perfectly simulated. So if there's somewhere between, say, like the previous limits of like 50 and 192 that you think you can get, exact, representations from quantum algorithms, then that's for you. So it's just, there's more restrictions. So on one extreme would be to replace all the gates and everything in the PQC or parameterized quantum circuit with some approximate of what all that just did, that runs more efficiently on a classical computer. And likewise for the embedding, instead of doing everything faithfully and, exactly, that it's an approximation of whatever the process is trying to accomplish. So it's kind of the only way. And most people don't, I started off running, dozens and dozens of, Qiskit and Penny Lane demos, and I'm just now getting to this, and this is more important than that. Any other questions? Feel free to put it in the chat as well. And if you're coming from any background, that's fine. I do receive, text and communication, kind of like there's a new paper out or they want me to see it, these types of things. And you just go to the conclusion, and that's where they tell you, it's still, if it's quantum hardware, it's still going to be in infancy. There's noise issues. And I just had one this week, and it says that we can't guarantee that it wouldn't run faster and better on, using classical algorithms or dequantized algorithms, those types of things. So keep an eye out for all this stuff, because I'm focused in machine learning, right? So this is for, a better customer or patient experience in medical. And, all of this stuff that leads up to, so when we talk about value, expectations, care, and essentially, changing the healthcare existing AI landscape with something that's more of a drop-in. This is software, right? And it's been proven, in multiple times in papers, and then especially with industry commitments too. And other hospitals, there's a Tel Aviv hospital with Classic in Israel that's, using quantum-inspired approaches too. And then anybody else? So Samuel or Anand, or yeah, Samuel or Anand?
Today, no.
Or Saket or Risky?
Oh, no. In fact, thanks for inspiring me to read more on Tensor networks. I started it, but I probably I should read more about it.
Yeah.
Thanks.
Yeah, I appreciate you coming on. And the heads up to everybody is this process up to this point. And again, I'm going to be, pivoting more towards like customer experience of now that it's been proven with, migration guides. And there was a review last year with quantum inspired machine learning that's fantastic. It's by Hoyne et al. So it's called Quantum Inspired Machine Learning, a survey. There was a lot that came up to this point, and then now kind of stepping back and say, okay, the most important thing is who's going to be using the technology. And then, based on all this great results that exist in literature and the commitments in industry and these types of things, then how can, what could be taken from all of this to improve, patient experience? And, the human AI team is what FDA calls this. So there's like at least, I think, 700 FDA approved AI ML algorithms, right? And they have specific conditions to meet, safe and effective, substantially equivalent to predicate device, those types of things. So if we're talking software and not just reinventing the wheel like other quantum technologies, then this is the approach to take. And I think, that it's hard to educate everybody coming from all these different angles. And again, if you were programming, quantum circuits in a different fashion, now this is it's a more relaxed, right? So it's less about the faithful representation of what the circuit you intended it to do on a classical computer. And it's more like, how can we use all these, quantum physics, quantum mechanics in the most productive way, like not using the whole Hilbert space, but using a part of it on, classical computers. So I think that's the fun and exciting part of this. And if you were to ask somebody, where the future of, AI or humanity, these types of things is, and I would say, it's a classical world. And to take quantum inspired techniques into that is another step that's already been taken with tensor networks. And we see that a little bit with dequantized algorithms, but it's what it'll come down to. If you envision the world in 5 or 10 years as completely different based on machine learning and AI, is that, with the multiverse research today with tensor networks and NYU, that university last week I reviewed, is that it's more and more so this classical world, and now we can inspire it with quantum mechanics. So I'll be, kind of like, that's the path, right? It's just the traditional business path. You have a technology, it works, many people are using it, and then, applications, these types of things. Yeah, so I think Risky put in the chat, he says, thanks for the presentation and very helpful. I hope this does help. I don't think it's the mainstream approach, but it's the one that's the most accurate, I believe, based on literature. And some industry findings, and you'll hear me talking about, Sandbox AQ, so they've committed to using GPUs for quantum inspired approaches, and, many others, have too. So, but yeah, any other kind of questions here? If you're stuck in between all this stuff, if you're doing machine learning and deep learning and you're trying to see how this fits in, I would be very happy, if I were you, because of the papers that have come out. And like with anything, you can learn new tricks, right? So I don't think it's as much inventing the wheel doing tensor networks as it is some other aspects of quantum, computation. Or say like dequantizing algorithms, those things would be more specialized. So then any other questions? Any other thing regarding industry news? Like, again, the Penny Lane Q hack was ending this week, and it kind of went on for a couple weeks. It started with the Quantum Jeopardy, ended with some memes today. So they always do a fantastic job. They've got a good group of people. Now, libraries moving forward, it'll be interesting because, the Qiskit approach was definitely more towards QiML 1.0 to design, software for an eventual quantum computer. And there are some Penny Lane demos, tensor networks. I've kind of modified that a couple of times. And that's a little bit more tamer than what you're going to see in literature. But you can ask for those things because, it's something that I think that's within the realm of what the quantum community wants, tensor network demos, those types of things. From last week, it was Julia that they were using a lot for contractions and all the, related tensor network, those processes that they used. It was Julia. It wasn't Python. So, and it looked like you could do a good amount using Julia for that specific application. And then we'll keep an eye on, dequantized algorithms and where they wind up. And one of the questions is, binary versus multi-class. And I think that's definitely within realm. We're talking about an efficient classical algorithm that's, freestanding. It doesn't need, any other, it could be used with other data, and some have restrictions as for low rank and sparsity, those types of things. Awesome. Any other last comments or questions? I appreciate everybody coming on. So again, this will be up pretty soon. And again, after I did this one, it's pretty clear that, you see the previous weeks, it was for the win as far as this is the technology to use for machine learning, quantum computing, sensitive data, going into many years into the future. So again, it'll be kind of, targeting and aiming more towards patient experience, customer experience based on this working technology. And I think the technical part of this is pretty good under the belt. Awesome. Okay. And I appreciate, yes, and the recording will be, and I'll put in the chat here. It's up on the channel. And you could probably find a very good amount based on these technologies. Let's see, videos. So I'm putting in the chat where it's going to be posted. And, if you go back a couple discussions, you're going to, let's see. I'll put a better one up in the chat here. So it's okay. So this one. Okay, so this will take you straight to it, the second one. And I just did a big spiel, so like a 5-6 minute spiel, earlier this week. Basically this is the approach, especially for sensitive data, and it scales and the performance and all that kind of stuff, and safe, effective, these types of things. So that's in the chat. I appreciate everybody coming on. So this has been event seminar 123 for basically QiML 2. So this is speed ups, scalability, and performance for the new machine learning era. Have a productive rest of the night and have a good rest of the week, everybody. Take care. Bye.
Thanks, Ken.